Welcome to my talk, Code Emulation for Reverse Engineers, a deep dive into radare2's ESIL. My name is Arnau Gàmez Montolio, and I'm a Maths and Computer Science student at the University of Barcelona. I'm also the president of Hacking Lliure, a Catalan non-profit organization around ethical hacking and social issues related to that. And I'm also one of the organizers of the radare2 Congress. Here you have my Twitter handles and my website in case you want to follow me there. So what's motivation for this talk? First of all, I wanted to force myself to essentially understand how emulation was working, and specifically how emulation was working within radare2, which is implemented with ESIL, the radare2's emulation engine. Also, I wanted to provide an easy introduction to ESIL for everyone around that wants to get into it and better understand why do we need it and how to take advantage of it. And last but not least, I wanted to show and demonstrate some of its application on practical scenarios. So I will look at it also. Here is briefly the outline of the talk. I will spend little time, hopefully, making an overview of radare2 just to make sure everyone is on the same page. And then I will go straight into the emulation part. Well, let's start with that. So radare2 is a free and open source reverse engineering framework, which is rewritten in C mainly by Pancake. Now it has a ton of other collaborators, but it was mainly written by Pancake. It's built from scratch without any third-party dependency, and it's also very portable, scriptable, and extensible, as we will see. Its release is every 6 weeks, and it's more or less the same way that Rust works. And of course, it has a great community. And we have the R2 Congress, which is the annual conference around radare2, held early September here in Barcelona. But this year we have the particularity that due to the situation, it will be fully online, and also it will be free. So be sure to check it out if you're interested in that. What are the radare2 capabilities? Well, very briefly, it can, of course, disassemble binaries of several architectures and operating systems. It can be used for analyzing code and data, as well as doing low-level debugging, and also it has some features to help us with exploiting. Of course, we can do all sorts of binary manipulation, and it has some features to deal with forensics, like mounting file systems, testing partitions, doing data curving on raw images, not assuming any format at all. Indeed, radare2, the name comes from raw data recovery. It was initially conceived as a forensics tool, but then it evolved with the needs of its main author and also the community into more of a general reversing framework. We can also extract metrics for binary classification with it, and with some plugins that it has, we can perform kernel analysis and debugging as well. So what's the formats and the operating system that radare2 has support for? Basically everything you see here. And I'm not expecting you to read it, but it's on the documentation on the GitHub page as well. Just runs everywhere, supports everything, just keep that in mind. And most probably if you find some architecture or some file format that is not still supported, it's very probable that it already is supported, but maybe they didn't update the documentation page saying that. So please check it out. Now, how to get radare2? The best recommended way is just cloning the repository, editing directly from the Git repository. Here you have it. And then for installing as well as updating, we have the sysinstall sh script, which will basically pull the last version from Git and automatically compile and install it for us. So every time you just want to update radare2, run this script and load it. So yeah, keep calm and use radare2 from Git. This kind of important, mostly if you're using some distributions with really old packages in their package manager. I'm thinking, for example, of Debian, that unfortunately has extremely old packages for radare2, the derivatives as well. So be sure to keep updated, because many bugs and many problems are fixed like for some years, but unfortunately some of the version on package managers that are not quite updated. So if you can, please use it from Git, or at least use the last release. So radare2 is basically organized in a few libraries that are the ones that implement some of the required parts for the framework, and then we have standalone tools that are the ones that expose those libraries functionalities, as well as of course the main shell, the main tool radare2 that gets from a little bit from all of them to combine in a full-fledged framework from just one utility. But anyway, we have all those tools, standalone tools that we can use by their own. And here I have listed some of them, as you can see. I'm not going to read through them, but here just mentioning them for you to see. Just in this slide, I want to make a little mention for the first one, radare2, which is just compiling tiny binaries, but it's, well, technically that is what it does, but essentially it's useful for crafting our own shell code. And then we have also the R2PM, which is the package manager, because yeah, as I said, radare2 is very extensible and we can create plugins for it, and it has quite some plugins already. So we can install them and manage them with its own package manager. And finally, the radare2 tool, which is the main tool, the shell that I'm sure many of you already know, which is the tool that exposes the functionality of basically all the other libraries and all the other standalone tools, but combined in a reversing framework integrated environment. So let's see, how can we spawn an R2 shell? First of all, notice that R2 is just a symbolic link for R2, and we will usually use that for spawning a shell. We can just open a file regularly. We can open a file in write mode. That is, we will be able to overwrite the contents of that file, and that will be stored directly on disk. Afterwards, in one of the demos, we will see that we can actually pseudo-write, pseudo-modify a binary that we have opened without the need to the write flag, and won't be stored on disk. With enabling what environment bindable called IO cache. We will see a little bit of it afterwards in one of the demos I will explain to you. Then if we want to debug the file, we will just call it with the D flag. It will spawn a process and attach to it, and will expose all the functionalities needed for making the debugging. Finally, we have here a few more ways of opening a shell, just not parsing user settings in case there are some defaults, and as well another two options to just spawning a shell but without getting any attached to any particular file. So this slide is quite important because it explains basically why you shouldn't feed radare2. Usually when someone first looks at radare2, and especially if you are watching someone who knows quite a lot of radare2, you just see he's throwing a bunch of random letters and doing stuff, and it looks like, oh, that's crazy, I will never understand. The point is, radare2 commands are based on mnemonics, so every letter has a meaning. And every letter that goes after that letter is just a subcommand or modifier of the command reference with the previous one. So here are some of the basic commands that we have in radare2, and with those we can already do a ton of work just with that. We can seek to an address. We can print the hex dump where we allocate it to an address. We can print the disassembly. We can write hex pairs. We can write assembly. We can analyze all code, and we can get the information of all the stuff, and we can of course quit radare2. So keep in mind that this is the format of the commands that we will be doing around that and during the talk, and of course during the demos, and that will be it. One of the important things to keep in mind is that the radare2 shell, the main tool, has an inline help bundled into the same shell, and you just need to append a question mark to any command or any subcommand to get that help, and it will show how to use that command, the parameters, all the subcommands, and so on. So it's very useful because you don't need to get out of the shell or go to the browser and look for that. Usually you have everything you need to know how to do some certain thing, just looking in the inline help. So some handy tricks that we can use with radare2 are the following. As you can see, we can append a J or with the formatting for the JSON output. This will just get us the output of the command that we are that is prefixed with a JSON format. So that will be quite useful, mainly combined with a scripting language that we will use that a little bit, and I will show you. Then we can append a queue for required output. It will just drop some of the verbosity of the output and get straight to the point. We can also make an internal grep with that symbol. Maybe some of you are asking, why do we need internal grep? Basically because we can pipe the output of the radare2 to shell commands just using the regular pipe. So some of you might think, why don't just pipe the grep? The answer is that not every system in which you are going to run radare2 or you're willing to run radare2 has to have the grep utility installed. So it's quite useful to have an internal grep for that. Finally, we can just escape to the main shell with the exclamation mark prefix, and it will just run as if it was in a shell. And we can do a temporary seek with the @ symbol. It will just place the others pointed, and in that case, in the example, it's just the others pointed by the flag main, and do the operation that it has to do. In this case, print the disassembly, but it won't seek to that address, so it will just perform the operation, but without changing the seek. That is the address that we are positioned in the right moment. In radare2, we have some visual modes that will be quite helpful while exploring the code and the hexam and so. Basic one is just pressing the V, uppercase V. We can rotate the printing mode with the P. That will take us from hexam view to disassembly view and so on. And if we want to get help within the visual mode, we can just press the question mark while we are in visual mode, and we will get the visual help mode. While we are in any visual mode, if we want to run a radare2 command, we just have to use a colon and then enter the command, the radare2 command we are interested. Then we have also the graph view, which is awesome, and it should be incorporated everywhere. And it allows us to just follow the function's flow, exploring the control flow graph of function. For it to work, we have to be seeked on a function, or just use a temporary seek on an address that is the beginning, or it's on a function. And we can move with the arrows of the letters, those letters. We can as well zoom in and zoom out with the plus and minus. And as in previous visual mode, we can change to the print modes with P. Finally, we have also visual mode, which is the visual panels. And those are quite useful when debugging. You have those panels where you have the disassembly and then the registers, the stack view, and so on. And we can customize those views for our needs. So this is quite useful in case you are making some debugging with radare2. That will be useful. Talking of debugging, just a few words about debugging radare2. Note that it starts debugging at the dynamic loader, not the entry point of the program. That means we can explore all the loading process before arriving to the actual entry point. Of course, this is a low-level debugger, so it's not aiming to replace any source code debugging, or it's not intended for doing so. And we have many backends. We have, of course, the radare2 built-in debugging capabilities, but we can just attach to a GDB server. We have plugins for using radar as a front end for radare2 for LLVM and for Frida. We have different backends that we can use for the debugging as well. So for debugging, as said before, radare2 is based on mnemonics. So under the D letter will be the debug commands, and we can see here some of the very basic ones. So you can explore, of course, all the rest, just depending on question mark after the D. But here we have some of the usual actions we want to do when debugging. And finally, about radare2, I want to just very briefly talk about scripting with R2Pipe, which is the de facto way of scripting on top of radare2. It's just a very simple API that it's available for many languages, and it will just require an input of radare2 commands that will get back to us the radare2 output. And of course, there is some cool stuff that it can perform the JSON deserialization into native objects. What means that if we provide as an input a command with the prefix J that, as I told you before, it's just giving us back a JSON output of the command, it will be able to decellularize that JSON output to a native object. To be more concrete, for example, in Python, we can just install with pip, and this is really simple. We just import that and then open a file, throw some comments, and if we want to get and we want to throw a command with a prefix J to get the JSON back, we can use cmdj. So it will, instead of returning us the output to the string, it will return it as parsed and decellularized JSON into a native object of the language. In this case, in Python, we will get a list or a dictionary of the information that it has given us back. So that was for the overview of radare2. This has been just to make sure that everyone understands a little bit how radare2 works, how the commands are constructed, how to open a file. So hopefully there will be not much people who lost the track during the emulation part. It won't be very hard to, it won't be hard to follow, but anyway, it's better if everyone is on the same page on that. So what's emulation? Basically, when we talk about emulation, we are talking about simulating the execution of code of the same or different CPU in our machine. I'm really sure that most of you are familiar with one particular kind of emulation that is used for running games from old consoles in our devices. That's basically one of the most common emulation usages. But in our case, why do we want and why are we interested in emulation? Is not to get a full-fledged emulation of a whole system, but more for in our reverse engineering mindset. We are interested in understanding specific snippets of code, so quite small chunks of code that we want to understand what are they doing, how are they behaving. We want also to avoid risks of native code execution. That is, if we want to see how see the behavior of some routine of some malware we are dissecting, and we don't know yet what they are actually doing. If we can emulate them, and it has some advantages because we are not actually debugging, and that means that we are not actually executing the malware. We just can't go to a very particular place in the code and emulate that just particular lines of code and see how is it working, and then extract some information from that without even executing. So it's a sort of pseudo-dynamic analysis, but without running the code at all. Also, it's quite helpful in the debugging and the code analysis part. In radare2, in some of the advanced analysis option, it actually uses emulation to see the behavior of functions and parameters and so, or to doing some of the analysis. And of course, we are able to explore non-native executables with some sort of pseudo-dynamic analysis. But if we are set on our Intel-based architecture and we want to explore some ARM or some MIPS or whatever, and we don't have a full-fledged emulator, we don't have access to a device of that type, we can just emulate the parts we are interested in and see how they behave. And we don't need to to have the native architecture attached or access to them. We can just work with the binaries, but without the need for a native device to explore them. We'll talk just a little bit about intermediate languages, and then I will introduce ESIL, which is the intermediate language of radar, as you might have guessed. So basically, just taking from the Wikipedia, an intermediate language is a language of an abstract machine designed to aid in the analysis of computer programs. What does that mean? So basically, it's a language that is built ad hoc, basically, that has some properties that help us with the design and the analysis of some algorithms and some methodologies for understanding and processing some parts of the chain, for basically compilation to compilation, but all kinds of analysis that we want to perform. That is, we can perform analysis on an intermediate representation of many different architectures. That is, basically, we're interested in some properties that affect very different set of architectures, and we want to treat them on a more generic way, not attached to the particular architecture. So we can leverage the use of intermediate language. The intermediate languages and the intermediate representation are vital for all that has to do with compilation and the compilation. Every compilation engine has some kind of intermediate languages where they process the code and perform the optimizations needed, and as well for the compilation, usually just get the particular architecture, translate it to an intermediate representation, and then work with that. So what is specifically ESIL? ESIL stands for Evaluable Strings Intermediate Languages, and is the intermediate language for the emulation radar2, and we also refer to ESIL as the emulation engine of radar2. Its characteristics are basically it's an intermediate language is composed with a small set of instructions, and the syntax is based on reverse policy notation, that is basically stack notation. I will show you just in a couple of slides a visual animation of that. And it's designed with emulation and evaluation in mind. So it's not designed to be human-friendly, reading all lines of ESIL, but for being useful for the emulation process and also for computers to process it. It has an infinite memory and set of registers. Theoretically, I mean, that is not limited by default. It's really common on other intermediate languages as well, this property. One cool thing about ESIL is that it gives us native register aliases. That is super useful when making some emulation. What that does mean is, for example, if we are emulating some x86, the register names that the ESIL engine, emulation engine of radar2 will give us will be the usual names that we are used to when reversing some x86. So that is, we will have names AX, ABX, ASP, AIP. So that will, and of course, not only the names, but the usual way they behave in the code. So that will be very useful for better understanding some piece of code that, for example, in contrast, if we just had the names register 1, register 2, register 3, it will be a little bit more complicated to grasp the idea of how some code is behaving, because we find, I mean, at the end we learn to reverse many times based on the, for example, the calling conventions and how do we pass parameters and what are the usual functions of some of the registers. So it will be very useful. Of course, those register aliases will be translated to another ones on another architecture. For example, in IRM, it will be R1, R2, R3, etc., etc. And finally, it's important to remark that we have the ability to implement custom operations and also calling external functions from ESIL. That is, we don't have, there is some architecture that we are emulating and is supported by ESIL, but there is some weird operation that is not one of the basics usually covered by ESIL and shared among the different architectures, we can just implement our custom operation and call it. So why do we want ESIL? First of all, as I advanced before, because we have the need for emulation on R2 and we want intermediate language that is easy to generate, parse, and modify, and that's the reason, because we're using reverse police notation, the stack notation, and also the extensibility part that I just commented. We want to be able to have a very flexible intermediate language, and finally, just why not? We can have one. We can take advantage of it. So let's just have it. So I will share with you now some visual explanation of how ESIL works, and just a few notes so everyone gets it better. And I like to call ESIL the engine as a stack machine on steroids. What do I mean about it? This is the diagram of what is a stack machine, or more academically known as a push-down automaton. And I won't go deep with computer theory, but basically what you have to know about it is that a stack machine or a PDA is just have an input symbol and the current state, as well as a stack symbol, and then there is a transition in which the state changes while manipulating that stack. And when I say manipulate, it's basically doing push and pop operation, which is what a stack data structure can deal with. So that is, with that idea in mind, we can just get to the parser idea of an ESIL expression. So we'll have some stack notation, reverse police notation, and this will be basically the parser of ESIL. As you can see, we just start reading the ESIL string, and we get the next element. If this is an operation, then we get the operation, perform the operation. Otherwise, we just push that element to the stack. Please notice that when we encounter an operation and we perform it, and while performing this operation, it will pop the previously pushed values and the symbols in that terminology, and use those as operands. And here you have an animation of that. Here is just the 3, 5, plus sign is just a valid ESIL expression. Very, very easy, but it will serve as our example for the sake of simplicity. Note at the bottom that I will just guide you through the algorithm of the parsing. So we are not at the end of the ESIL string, and then 3 symbol is not an operation, so we push that to the stack. Then again, we are not at the end of the ESIL string. The 5 symbol is not an operation, so we push that to the stack again. Now we are not at the end of the ESIL string, and the plus symbol is an operation. So we will perform the operation by first popping the values of the stack, the previously pushed values, then perform the operation and get the result back. That's basically how ESIL works for every operation. This was, of course, very simple, but it's a valid operation, and it's the basis of how the syntax of ESIL works and its operation. We can play with those expressions directly with the radare2 shell. We just need to use the AE, which stands for analysis ESIL, and then we just give it an expression, an ESIL expression, and it will compute it for us. We can check that. So we'll radare2 shell without touching to anything. And that's it. It will give us back the 8, the result. So, okay, we have a push-down automaton, stack machine, but we want to push it a little bit further. So what's the idea behind expanding its limits? Basically, as I said before, asteroids. We need some asteroids, aka cheating, if you want to say it that way, but it's basically some asteroids added to a push-down automaton to let us be closer to a Turing machine. What does that mean, the asteroids? First of all, asteroid number 1, at random access operation. We can go to a specific place in the ESIL string parsing. And as well, we have control flow operation. That's basically if else control flow kind of the operation. It will basically be bundled into ESIL as well. And the storage part 2 is we will have register access, and as well we'll use an extra tape with random access, which will be basically the virtual memory of the virtual machine stack. At the end, ESIL what it's doing is constructing a small VM that will have mapped some registers, and if we need to emulate operations that are using what would be the memory, we'll use a virtual memory an extra tape that will be that little VM stack to perform those operations. This won't be needed all the time. For example, if we want to emulate just a little snippet of code that is just dealing with some registers and storing the value in them, but not touching the memory, that won't be needed. But in case we need it, we can add that extra tape. We will see how to do this. So this is the practical usage about ESIL, which is what most of you will be interested, I guess. And as I said, ESIL options will be under the AE command, which is analysis ESIL. We can do a bunch of comments. First of all, init, which is basically initiating the emulation engine. This won't initiate any extra tape, as I said before. But if we need it because we are performing some memory operation, we will just use the IM, which will init the memory. And if we use the IM, we won't need to make the init before. It will be redundant. Then we can set the instruction pointer, and we can do some things quite similar to the options, the subcommands we had while debugging: stepping until, showing the register, stepping over. But there is here one that I want to specially mention, which is the step skip. And it will basically skip instruction or a call to a function. And while skipping, I mean not stepping over, which is like performing all the operations inside, but not going in to explore it. But a step skip is literally skipping that part. For example, if you are emulating a snippet of code that has a call to printf, printing some of the code, we just are not interested on emulating the whole printf call, which will be quite expensive and useless. We can just skip that part of the emulation and emulate the rest without having any problem. So what are the ESIL operands? I could have shown here a massive table, not that massive, but quite big table. But the best thing is just check them on the radare2 shell, and we'll see descriptions and examples of them. I'm gonna show you that just right now. So here you have the different operands of ESIL. Here you have assignation, then and sums, incrementing, then other kinds of access to memories, etc., etc. We have some other here, as you can see. And one of the, for example, we have the go to that I told you before in the storage part 1. We have the control flow one. This basically will implement if else kind of control flow. And you can check those. You can check those here. We have some examples, description, and so on. Finally, we have some internal variables, which are basically the flags, which are prefixed with the $sign. You might have seen them just here, just at the bottom, those in there. And those are updated on each operation, and these are used to set the flags for every particular architecture. You might be wondering, why is it that you need to update those manually on each operation? That is, why don't, if you just make a subtraction, automatically update those internal variables flags? And the answer is that not every architecture updates the flags in the same way. That means not every architecture sets the different flags at the very specific moment and in the same circumstances. So you basically have the translation between one architecture, how it implements the flag manipulation, and its ESIL correspondence. And they will be updated at each operation, but depending on each different architectures, they might be updated slightly different. So that's why they are not made in a generic way, because that won't match all architectures. And finally, let's go for the demos part. That will be probably the most interesting part of the talk. First of all, let's defeat a very simple crack me. Let's do this. Okay. The crack me is very, very simple. It's usual, very usual kind of crack me. It's print some title, then ask for a password. We put it, and it says invalid password. Okay. So let's just open it with radare2. We will analyze everything. Then we will print the disassembly of the function. Which function? The one pointed by the flag main. And here, as you can see, we have the reference to this string, which is the title we just seen, then a call to printf that will print that string, then another reference to the string password colon, and then another call to the printf, which will print the password message asking us for the inputting. And then we see here a call to scanf that will effectively store our input in var4h. var4h is just an internal flag name for the variable stored at evp minus x4. So basically, here we can see that there are some operations being done in this particular snippet of code. At the end, we have a comparison and a jump, a conditional jump. So check that we have our input will be stored in var4h, and then there is the comparison between ax, which has our input, with the value pointed by var.ch. And in var.ch, we will have here the result of those operations. So basically, it will be comparing our input with the result of this, all the operations in this snippet of code. If they are not the same, then it will show us that there is an invalid password. Otherwise, it will show us the password is okay. So what's the deal? It's a very basic crack me. The only thing that it's doing is doing some computations, very, very simple, but anyway, some computations with that, and then making a comparison with our input and checking that input and doing a conditional jump depending on that. What can we do to extract the valid password for this crack me by using emulation? So basically, we can start our emulation just in this line where it starts loading some values and then do some stuff with them, which is just after the call to scanf, and emulate until the comparison is done, and then just check what is the value stored in var.ch, which will be the outcome of those computations. So let's just do that. Let's first of all stick to the others where we want to start the emulation. Then we will initiate the ESIL engine as well as the VM stack with IM. Why I'm initiating the virtual machine stack? Because we are performing some operation that involve dealing with memory references. So we will need that extra tape that will serve us as our memory references. Now, as we were already sicked where we want to start the emulation, we won't need to set the instruction pointer in there because it will be already. But anyway, if you need it, you can just set the instruction pointer to the current SIG offset with this analysis instruction pointer. Now I will show you the state of the registers. Those registers are the registers of the ESIL engine, not any debugging is going under the hood at all. So these are the registers just for the ESIL stack. As you can see, we have the instruction pointer just here in the address we are located. And then we can see that because we have initiated the ESIL engine with the virtual machine stack, we have initiated the stack pointer and the base pointer that will give us that stack virtual machine to play with. So that will be it. We will just need to emulate until this address with analyze the ESIL step until this address, and it will emulate from where the instruction pointer is located to this address. That is basically emulating this particular snippet of code. Now it has been emulated, and we just need, I will show you the registers. We have some changes in the EDX that have been done in those computations. And of course, the instruction pointer went to the address that we emulated until. So now we just need to check the value that is stored in var.ch, and basically we can do that getting this is the memory region of var.ch, and we can, for example, just print formatted data, and which format letter D. It works same way as in C, D as in decimal, where just here. There will be a temporary sig to that memory location, printing the format data as decimal. So here we have it. That will be the value stored at the memory address reference that has the outcome of those computations stored. So basically, we can just now get this value, run the crackme again, and voila, password okay. That will be our first example. Okay. Let's see another example where we will use combined the power of the emulation with ESIL, as well as some basic scripting with R2Py. We'll be using Python, and just to brute force, to show that we can actually brute force some values with that approach. Sorry, here. Okay, this is a quite more involved crackme, and I won't be solving it all the parts, but just for you to know, it asks for a magic number. It looks like we will input some random numbers, and you can see it says that is bad. So let's just open it with var2. Okay, let's analyze it. Then let's just open the graph view. Remember, it was for the graph view, and where? Well, we want to see the graph view at the main address. Now, if we press P, I will press P, so we will change the print mode. In this case, it will show us the addresses. And here, just look again at this reference to that string, which is the give me the magic numbers we have seen, and the printf to print that string, and then a call to scanf, and it will be storing our input in the memory address reference by this size. Radar has changed this, how to name this name to this variable reference to size, and we will see why afterwards. But we are just interested in, okay, it will move this to ECX, and it will do some computations and test, and finally make a test. So basically, look at this test instruction. It will basically be 0 in case that the previous abstraction was between two equal values. That basically means that that EAX, which is loaded with ECX, where it was stored our input afterwards, and the EDX, which is the register where the outcome of those computations will outcome the result. So basically, if the outcome of those computations compared with our input, that will be stored as ECX, and then here is moved to EAX. If they are equal, then EAX will be set to 0, and if EAX will be set to 0, then the test will pass. And by passing, I mean that it will go to the next basic block that we are interested in, that is the one that is not bad. Indeed, the test won't pass actually, because it will be equal. So anyway, if our input and the result of those computations are equal, then we will go to this basic block in here. Otherwise, we will go directly to the bad basic block, the one that will print us the bad, and we'll just exit. So please take a moment to check that in this basic block in here, which is the one we want to go, we have another weird comparison, or at least not weird, but looks like strange that after this computation and the first comparison, the first testing, we are just loading our input in EAX and comparing against x14 hexadecimal, which is basically 20 decimal, and then if it's below or if it's lower or equal the 20 of our input, then it will go to the basic block we are interested in go, because we see here tell me more, and we can guess this is the right path. So after the first check we have seen, then it makes a second check to see if our input is less or equal than 20. And if it's not, it will go again to the bad message. So what do we know about it? Basically, that anything that is computed here and any outcome that comes from here, it should give us a number that is below 20, because otherwise it will go to the bad message anyway. So we can just brute force it, because we just need to try until 20. We just have 20 values to try and see if this works, and the test is successful, so it goes to this basic block, and then it has to be below 20 for it to succeed. So let's just brute force it. I will show you a simple Python script that will make it, and I will explain you a little bit. So basically, I'm importing the R2 pipe, I'm opening the file, then I'm initiating the ESIL engine. Now, please take a look that we are not using any reference. We will not be using any reference to memory location, so we don't need to initiate the virtual machine stack. So I'm not using IM, just I will be enough. Then for range in 20, we just set the register ACX to the value of the range, then seek to 90E, which is basically the start of the snippet of code we want to emulate. And we will place the instruction pointer in here, then step until 90C, which is basically just before this abstraction, and check if the value at EAX and the value of EDX are equal. That means the value of the outcome of those computations with the value of our input are equal. In case they are equal, just we print we have found a candidate magic number. So let's just run it and see how it works. It will, of course, go in a loop until incrementing our input value, what will be our input value stored in ECX at its iteration. So we just run it. Please note that I'm just calling the standard shell from within radare2 by prefixing an exclamation mark, as I explained you before. Here we have. So it found two candidate magic numbers, and I won't go deeper into this reversing challenge, but I will just tell you a little bit that we can literally drop the zero candidate, because as we will see here, it will use this input just for making for passing as a parameter of a malloc, and then it will check the second input, our input after tell me more, to be at the size of maximum size of the first input. So it will make no sense for it to be zero. But anyway, that's a task for you to follow. If you're interested, I have a complete write-up of this challenge in my website, so you can take a look at it or just try it by yourself. We can just see that 17 works, and we go to tell me more, and the next is work home for you. And the final demo will use ESIL to deobfuscate some encrypted code, This will be quite interesting. This sample is taken from a sample of one reversing book, Secrets of Reversing by Alan. So basically, let's open this file, Defender. We will analyze everything, then we will just list functions. In this case, we don't have a main functions. AFL is just analysis functions list. So we will see at entry 0, what do we have? And just after, just very beginning, we have a first function call, which does nothing. I will go there just by pressing OA will go lead us to that function. It's just setting some, digging into some structure of the how's that, of the threat environment block structure, which is referenced by the segment, blah blah blah. We're not interested in that. It's not the point. You can check this, all the following of this example in that book. But anyway, what we are interested in is the second call. If you look at, I will go just there now, and I will make it a little bit. Zoom out. So even if you can't read it, it has a very strange form, this function. Look at it. So it's basically like quite symmetric function, and we have some weird thing that I will show you just here. That, look at this comparison. It's comparing var 8 with 0, but just after putting a 1, so it will always be false. So it will always take these primes. What does that mean? Well, I will explain you afterwards. But anyway, this looks like it's setting some values in here, which is this address and also that address, and then we'll be using those in here. Okay. What's the deal? What's the deal? Look at this address. Okay, I will just now print the addresses of the functions. You take a look at this address, the 34DD. Check that this literally the address that will come after the last instruction in this function. So let's explore it. Let's explore it for a second with a visual mode, for example. And let's just move to this assembly. So here we have the end of the previous function, just in here. And indeed, there start a set of instructions that doesn't look that they make much sense. We even have some invalid instruction and really weird instructions in here. So basically, what the function we just seen is doing is decrypting the code that comes just afterwards, starting from this address until the other address reference that we have seen before. What can we do to decrypt that and retrieve the actual code without having to debug it? First, I will just show you that we are dealing with check this. We are on this is a Windows executable, so it's a P of 32-bit. So basically, we are now on a Linux machine, so I shouldn't be able to debug it. And anyway, we will be able to analyze it and even deobfuscate the encrypted code with the emulation. How can we do this? So let's just again list the functions. If you remember, this was the function that was performing that. It was just before the encrypted code we have seen that looked like it was doing the encrypting and decrypting process. So we'll just seek in there. And then now I will enable the IO cache. And this is what I told you at the very beginning, that we have a way of kind of writing on the binary, but without modifying the file in this. So this is the way. This will just enable as a cache for modifying the representation of the binary, but just for the session. So it won't be stored on disk. And this will be needed because we will be modifying the binary itself. Then initialize the ESIL engine with the VM stack initialized as well. And finally, we will just step until the end of that function. Remember that we had that the 34DD was the beginning of the next of the obfuscated code. So just the previous instruction was DB. So let's do this. We take a couple of seconds, and that's it. Now, if we open the visual mode here, we can see that after the end of that function, the code that previously was garbage now makes sense. Okay. So this is cool, but which is cooler is that we can actually put that on an initialization script to do this by default just when loading that file. And this looks like that. It's just a simple text file, plain text file that will perform the emulation that we have seen. It will just analyze everything, seek to the function, enable the IO cache, and initiate the ESIL engine with the VM stack, and then emulate until the end of that function. That will effectively decrypt the code that follows that function, as we can see. So we can use this file as an initialization script for the radar2 session. So it will execute those commands in order just after giving us the session. And that will be it. Just as simple as that. We will open a session to analyze this file, but without the encrypted code. Sorry. Yeah, here we have the decrypted code. If you are wondering about the comparison I told you before, it's just after the decrypted, this comparison, I mean that moving one and then comparing with 0, it makes no sense. This comparison is basically because, as you might have guessed, this part is the decrypting part of the code, and after this decrypted code finishes, it will re-encrypt itself with this other part. So we will have at the end moving 0 to that variable and jumping just to this comparison. So it will go to the other branch of the code to re-encrypt itself after it's finished. Just if you are curious about it, I encourage you to take a look to this example and also following the guide with the book, and you will understand way better this example. But I just wanted to use it for showing that we can actually use ESIL with non-native executables. This one is a PE of 32 bits Windows executable, and we can do some pretty interesting stuff without executing anything. It has no debugging at all in here. Well, that will be about it. Just to point you to a few cool things with ESIL that have been presented recently in the past radar2 Congress. Here we have a talk by Conrad that this was ESIL applied for graphs and analysis, and it's quite interesting. I encourage you to look at that. And also another one about faking Windows data structures for ESIL to parse. Another very cool talk. So if you're interested in more applications of ESIL, you can take a look at those. And well, that will be it. Thank you all for watching this talk. And if you have any questions, you can leave a comment or just ping me at my Twitter, or you can just send me an email to the address shown. I also let you hear the addresses and Twitter handles of the projects I'm involved in, the Hacking Jira and radar2. And that will be it. If you have any concerns, any feedback, I will be more than happy to listen to them and to chat with you about it. Thank you very much.